part of the lecture we are going to discuss global vector, or in short we call GLOBE. So main idea of GLOBE is to use global co-occurrence statistics as well as the linear relationship among the vectors representing words. So see, in the previous lectures we have discussed about these different types of the co-occurrence matrices to obtain, and using those co-occurrences matrices we can represent documents, we can represent words. And that if you see, those are actually looking into the global statistics, in the sense that those numbers are being whether it's a TF-IDF vector, the values, or it's a raw frequencies, whatever the values comes, it's coming from the global sense, in this in the sense of you are considering the entire corpus or entire collection of the documents, and then you look into it. So even though, for example, you are considering a word context matrix, and then you are considering a window around a window of n words around your target words, so you can see that this is a local thing. But then when you are going to accumulate all those raw frequency or TF-IDF based on the entire collection of your documents, so in that sense it's a kind of a global statistics is being calculated. So the idea of GLOBE was, and it's a very recent method, and it has come after the word2vec kind of a model has come, although I have not yet discussed word2vec model, because that will be the next part of the lectures when Dr. Amit Avekar will start taking lecture. He will discuss about the neural models and all the models related to the which uses neural network models. So you will see that the word2vec models actually more focused towards considering a local context, and the next other thing is that they focus more on the or in fact not indirectly they focus that one, but when you look into the relationship which the resultant word vectors gave, they obey a lot of these different type of the vector relations, the vector algebra which you can perform on them, and it follows many of those relationships. On the other hand, the methods like latent semantic indexings, those vectors fails miserably to show this kind of a linear relationship. So the idea of GLOBE was to use the global co-occurrence statistics as well as this linear relationship. So that is the main idea of the GLOBE, and we are going to discuss that how the GLOBE is actually going to combine both these things together. And to begin with, we are going to consider the term context matrix. Some notation. So X is our term context co-occurrence matrix. Xi is basically the number of times any word appears in the context of word I. Basically, you are taking the sum over the ith row, or for the ith row you are taking the sum over the entire columns. And then the Pij is basically the probability of word J appears in the context of word I, and that the maximum likelihood estimate of that probability is given by this. So that we have you can again figure it out. So it's a Pij is probability of the word J appearing in the context of target word I. So hope this notation is clear. Now we will look into the example or intuition behind the glow. Uh, so the main idea again in the glow is, or intuition is, to look for the relationship of the two words with the help of the context words. So let's consider that we are looking for these words ice and steam, and then we look for few context words around these target words ice and steams, and look at the ratio of the probabilities. Okay, the probability of seeing the context word K given ice, and probability of seeing a same context word given the target word steam. So now here there are 4 examples of the context word we see, and in the first example what do we see? That this ratio is very high. It's significantly high than 1. The second example, the gas, is it's a very small compared to 1. And now if you look into the word water and fashion, they are very close to 1. So now if you see, see the word water and the word fashion. So water is related to both ice and steam, and that is why this probability is close to 1. So, and the same time, the fashion, which is neither related to ice nor related to steam, and that is why again this word is this ratio is equal to 1, or equal to 1 means that it's a very close to 1. While the words which is related to the more related towards the target word ice, which is in the numerator, this probability ratio, or this ratio of the probabilities, is very high. And if it is related with the gas, then related with the, let's say, the word steam, then it's very small compared to 1. So it's, what we see is that the words which are related to the target words, and with this ratio it is able to discriminate, we are able to discriminate between these two target words by looking at the context word. The solid says that okay, this word is more related to the target word ice. The gas says that okay, this word is more related to the steam. And if something which is not related to any of these words, then those values are very close to 1. So what do we see here? That this ratio allows us to discriminate between these target words, help to identify that which of the words are going to be very related to these target words, and which, and if some words are more related to one of the target words, then how this ratio is going to behave. Based on that, we can sort of understand. So by looking at this ratio, they say that, I mean, their hypothesis is that instead of looking at so if you want to understand this distribution relationship of the two words, then instead of looking at the direct probability like the Pij, the conditional probability, we should look into the ratio of these probabilities with the help of third word or the context words. So then they have proposed that any kind of a the expression we want to look at, they have to kind of behave in the similar fashion this ratio works. Since our objective is to obtain a vector representation, so we have to have defined a certain function over the target words and in the context word. So see that again there's some sort of similarity. You have to always see that while we discussed about the co-occurrence matrix and the term context matrix, there we saw that again for every word you can see that there could be a two representation. One is with respect to the row, which is a target word representation, and one is with the column, which is the context word representation. Similarly, here also we differentiate between that what is my target word and what is my the context word. So since I am looking at the target words I and J, so I consider their the target word vector representation, and K is the probe or the context word, so I am looking at the context vector representation. So now let's look into the this expression and then ask few questions. That first of all, this right hand side, what we see is a scalar quantity. So now the question is that we have to find a function f which will operate on these vectors and give us the scalar quantity. And what we also want that these vectors should have this linear relationship. See, our dual objective while defining the globe was to use the global statistics, so that we have used in the right hand side. Now the second is that to look into this linear relationship among the vector representations, so that we have to reflect somehow in our left side. So that this linear representation has to come into our left side, and then we have to find an appropriate function f which works over these vectors and give rise to a scalar quantity, and then at the end we want to come up with an equation so that we can try to either directly solve them or use some other methods to obtain finally these vectors. Because see, the right hand side is known, these quantities are known based on the corpus we are using, and these are the Wi, Wj and Wk. These are the things which we are interested to find out. So those are the parameters, you can say, parameters of the models that has to be estimated somehow. So now let's again look step by step. So one of the easy way to do is that you want to describe linear relations. You take the simple operations over them. So Wi minus Wj and the Uk. This is the context, and this is my target word vectors. Then of course these vectors can be made scalar with multiple kind of an operations. I mean, there's a plethora of options available, but what the authors of Globe used is that they have taken the very simple thing that okay, I want to take a dot product between this difference vector of Wi and Wj and the Uk. So now this is a dot product, and then this is a scalar quantity, and then this has to be equal to this. Then what we see is and now this is another kind of a little bit of a tricky step they have done, and So what they wanted to do is that any kind of an operation you do it here, that should be also uh, so here you can see that basically this is a addition operation you are doing, and the right hand side, because there is a sort of division or the multiplications is involved, so you want that whatever you obtain, once in the left hand side, that operation should be sort of preserved if you perform this multiplication, and that the required property can be ensured using this algebraic notion of group homomorphism. So all of you are aware that what do you mean by the group. Okay, so basically that you have a set and a binary operation, and that has to satisfy certain properties to be called as a group, and the group homomorphism, it says that you have a function, so between, let's say that the two two groups, so let's say that there is a group G1 to G2, and if you perform anything on this particular group, any operation on G1, because then G1 has its own binary operator, so let's assume that these are the elements of this set, and that has to be sort of preserved in so if G2 has the operation of multiplication, so that needs to be preserved here. So that's what the group homomorphism means. So we can define this group homomorphism because we know that the left hand side, we can consider that as a group, as a real number, and with the addition as a binary operator, and the right hand side with all positive real numbers, and the multiplication as a binary operator. So what we are looking at is that we should have this F as a group homomorphism with these two groups. So essentially it means that if you look into this operation, it's basically Wi transpose UK minus Wj transpose UK. So that is being performed on this group R, and it has to be sort of this preserve the group operation of this. So that is what this homomorphism means, and if we are able to do that, if we are able to find a function f which satisfies this, then our job is done, in the sense that we can say that this f of a, or the numerator, we cannot as such directly say that it's equal to, but it's kind of an approximation. We can say it's a kind of a proportional, but for the sake of, let's say that the simplicity, they say that this function should now equal to this probability, and we know that this pik is equal to xik divided by x. So whatever we have discussed, this leads us to the group homomorphism property leads us to this. That leads us to under the simplified assumption that we can write this f of Wi transpose UK is equal to pik, which is equal to xik and xi. So now we have to find out a function f, and in this case they have chosen exponential as an f. So if we put exponential here, this equation can be written like this. Now So we are at least, we our objective was to come to an equation. So that has been sort of achieved to a certain extent. It's still not really done. So okay, here is some correction. This should be K, not J. So now our choice of the word and context vectors are arbitrary. So why we can, if we replace anything as a word and a context vectors, we should expect the similar kind of expression. And but what right now we see that this equation is not really symmetric with respect to the context vector and the target vector, because this log of xi is only dependent on the target vector I. So if you modify this equation a little bit, by adding a term which is sort of reflecting that presence of the context vector, or you can say that the bias associated with, so this is a bias associated with the target word vector, target word, and this is bias associated with the context word. Then this expression becomes kind of unsymmetric with respect to both the word and the context vectors. So then now what we can do is that we can say that any kind of a word vector representation we should look, this should lead us to, of course, all of these things in the left hand side are the parameters of the model. We don't know anything, we don't have any values with them, so we have to obtain these values. And what we do is that to obtain these values, we define a loss function which says that we want to kind of find a wi, a uses, bi, and bk tilde, such that this cost function is minimized. Okay, so it has to be as close to the in this case, since we are saying the wi uj, so this j is fine, this j is fine, but in this equation this should be k. So wi uj, so the cost function with respect to that we can define in this fashion. So we want this to be as close to the log xij. But if you see the log xij has again the problem that if you look into the term context matrix, you are going to see that there are many of the entries are actually zero, and that creates a problem for us. So how to smoothen this cost function? So again, there could have been multiple choices, but then instead of that, they have decided to use a function, sort of take this weighted cost function, and so the idea of this this weight is that overall you want this equation at x equal to 0, it should it should vanish, it becomes 0, and if you x is going towards 0, then this entire the fx and log square x as your limit extends to 0 should sort of become a finite. So with that objective they want so that's what their objective was, so that this function remains defined at x equal to 0. So they have taken fxij, and again so this function can take multiple form, and although they have not really discussed that why particularly they have taken this, my expectation, my assumption is with the various choice of this function, this function might have given the better result for them. So they have considered this function. So you can see that at x equal to 0, this fx ij becomes 0, and that actually takes care of the smoothing condition. So with this, and so now there are two hyperparameters. You can see that one is that alpha, which again they have said in the paper that they have taken alpha is equal to 3 by 4, and x max is taken as I think 100. So these two values, these hyperparameters, they have considered, and then they have shown that that gives perhaps the better result. So with this choice of the weight function fx, now the final cost function can be written like this. So because you want to look for all of the words, so it's basically now this ij goes from all words in your vocabulary, and then you want to minimize this whole thing. So that's what, so basically this is the cost function which is being now minimized. So minimize over these parameters wi, uj, vi, pj, tilde, and just to sort of indicate that this is with respect to the context vector. And so basically you are looking for arguing that which of these parameter value gives you the minimum things. That is what ultimately gives you the vector representations for the corresponding words. Again, this can be solved by using one of the optimization techniques. You can use some gradient descent methods and then so on. So but the primary concern is that why they have obtained or how they have obtained this cost function. So ultimately, to implement GLOW, basically you have to just collect a corpus, find these xij's, you create your term context matrix, and then fit into this equation and optimize this equation. So you don't have to do any of these steps what we have discussed. This is just a discussion to sort of show that how you actually arrive to this final cost function. So that's about the GLOW, and that with this we come to the end of our discussion on vector semantics. But I think Dr. Amit Avekar will going to discuss the models like word2vec later on. So, but for the time being, our discussion on the vector semantics ends here.